Hey guys, Professor Calculus is here, and today in this video we're gonna see how we should solve this integral. Before that, make sure to like and subscribe as it is free and you can always change your mind later. So first of all, I'm gonna remind you of a formula that you've already seen. E to the ix equals cosine x plus I sine x. And you see that we have a cosine x here and a cosine x here, but the problem is that we only got the real part of this thing right here. So how should we proceed? In math, if I say the real part, RE of e to the ix, is the same as just writing the cosine x, just the real part of it. So if I just want to investigate on the real part of something, I can write RE of something. Now here, we want to have this real part of this integral as in terms of e to the negative something, because we want a convergence since our integral is improper and we want some convergence. So whenever we want a convergence, we want e to the negative something. And if I write e to the negative ix squared is the same as cosine of negative x squared plus I sine of negative x squared. The cosine function absorbs the negative sign because it's an even function, so I'm going to have cosine of x squared minus I sine of x squared, because the I gets out of the sine function because it's an odd function, and we can write this e to the negative ix squared as that. And now if I take the real part of it, the real of e to the negative ix squared, it's going to be cosine x squared. Now this integral here, the I equals the total area under this curve, you can write it as, since it's an even graph, you can write it as 2 times the integral of 0 to infinity of cosine of x squared dx. And since the real part of e to the negative ix squared is cosine x squared, I can write it as 2 the integral from 0 to infinity of the real part of e to the negative ix squared dx. And thus I can write it as 2 real of the integral from 0 to infinity of e to the negative ix squared dx. Now this seems to be like a Gaussian integral, and actually there is a really clever way to solve this integral. So what I'm gonna do right here, I'm gonna say, I'm gonna actually write this integral once more, but this time in terms of e to the negative iy squared dy, and I can multiply these two integrals together here, and thus I'd have I squared equals, for the real part of the integral from 0 to infinity e to the negative x squared dx times 0 to infinity of e to the negative y squared dy. And when we have two integrals multiplied by each other, we can write them as a double integral like this: e to the negative, forgot I here, negative ix squared minus iy squared dx dy. And I squared is for the real part of the double integral of from 0 to infinity e to the negative I times x squared plus y squared dx dy. Now we cannot proceed further here without using polar coordinates, but there is a way actually to solve this integral without polar coordinates with Laplace's method. So we were going to use Laplace's method. I'm going to let y be equal to xt, some parameter, some arbitrary parameter, and my dy would be dxt if I differentiate, dt x dt if I differentiate differentiate with respect to t. Now my dy is here, and I can replace it as x dt. My I squared thus is for the real part of the double integral e to the negative I times x is 0 y, it's x squared plus x squared t squared dx x dt, and I can move this one here. Thus I squared is for the real part of the integral from 0 to infinity x e to the negative I, factoring out x squared 1 plus t squared dx dt. Now I'm going to take this integral and we're going to work on this one here, right here. The integral from 0 to infinity of x e to the negative I x squared 1 plus t squared dx. Actually, this integral is solvable with the chain rule that we have learned in high school. So the u substitution that we've learned in college. So u is, I'm going to let u to be ix squared 1 plus t squared. Du thus is 2ix 1 plus t squared dx. I'm going to multiply it by 1 over 2i 1 plus t squared, 2i 1 plus t squared, 2i x 1 plus t squared e to the negative ix squared 1 plus t squared dx. So let me show you the parameters that I multiplied and divided by in other color. Let's say in this color, or in this one. 1 over 2i times 1 plus t squared, and then our integral 2 I 1 plus t squared, and then our x e to the negative ix squared 1 plus t squared dx. And here this part and this whole part is my du, and this part is my u. It's going to be 1 over 2i 1 plus t squared, the integral from 0 to infinity of e to the negative u du. I can go ahead and verify this integral does indeed converge to 1, and thus I'm going to have 1 over 2i times 1 plus t squared, which means the integral that I had here, I squared, is 4 times the real part of the integral from 0 to infinity of 1 over 2i 1 plus t squared dt. Now these two are going to go away. I'm going to be having 2 times the real part of 0 to infinity over 1 over 1 plus t squared dt. Now this here is the derivative of arctan of x. Thus my antiderivative would be arctan of t from 0 to infinity. Arctan of infinity is pi over 2, and if you calculate this limit, you're going to get I squared is 2 times the real part of pi over 2i, and you're going to get I to be equal to the real part of root pi over I if you solve for it. Now, we got a problem here. We cannot say the real part of this thing. We cannot say the real part of root pi over I is root pi. This is wrong. Instead, we have to have this thing here as a complex number. So I'm going to use a trick here. I'm going to say the I is actually indeed equal to the real part of root pi root I, and it is the real part, sorry, write it in the proper color, the real part of root pi I to the negative half. So it's supposed to be to the negative, supposed to be I to the negative half here. So what is I to the negative half? Just if you recall this formula, the Euler's formula, we're going to use this one. I want to see if I have a number, complex number, e to the ix something. When is my x equal to I to the negative? What x would give me I to the negative half here? Which means what number would give me negative 1 to the a quarter, because the square root of negative half of I is negative 1 to the negative quarter, ix. And if I take the natural log of both sides, natural log of the both sides into the ix, negative 1 to the negative quarter, ix ln e is going to be negative a quarter ln of negative 1. And natural log of negative 1, again, since we know negative e to the I pi is negative 1, we can write this as ln of e to the I pi. Thus we're going to get I pi ln e, which is the same as I pi. So I can write this as ix equal to negative 1 over 4 times I pi. The i's are going to go away, and x is going to be negative pi over 4, which means that e to the negative I pi over 4 is the number, complex number, that would give me 1 over root I, or negative 1 to the negative 4th. Now, if I write this integral here again, the I is the real part of root pi e to the negative I pi over 4. Now, using the Euler's formula again, e to the ix is cosine x plus I sine x. E to the e to the negative, to the negative I pi over 4 would be cosine of negative pi over 4 plus I sine of negative pi over 4, which would be, this negative is going to get absorbed. It's going to be cosine of pi over 4 minus I sine of pi over 4. Therefore, it would be root 2 over 2 minus root 2 over 2 I. And it's going to be root 2 over 2 1 minus I, e to the negative I pi over 4. And thus, the I is the real part of root pi times root 2 over 2 1 minus I, which is the real part of root pi root 2 over 2 minus root pi root 2I over 2. Now the real part of this number, we can actually say it is just root pi root 2 over 2. Can get rid of this one, and we can write it as root 2 pi over 2. Moving this under a radical sign would be 2 pi over 4, which is the root pi over 2. Thus, the integral that we were working on here, from negative infinity to infinity of cosine of x squared dx is square root of pi over 2, and you somehow see that the integral of 0 to infinity of cosine x squared dx is written as root pi over 8. This is because that these two are even and odd functions. This one is the twice this one, and if you multiply by 2 and move under radical sign, you're gonna get this result as well. Thus, we concluded that the total area under the graph of cosine x squared dx is square root of pi over 2. And that concludes our today's video. Thank you for watching this video. If you enjoyed, please like and subscribe, and I'll see you next video.